In this last lesson about the derivatives of trig functions, we're going to look at one of the most dynamic, literally, intersections in calculus. This is the realm where trig functions meet real motion. And if you're a physics geek like I am, this is going to be right up your alley. So this is where higher order derivatives reveal the hidden layers beneath the motion of our everyday lives. Think about a pendulum swinging or a spring oscillating or the rise and fall of sound waves. What do all of these things have in common? They can be modeled perfectly by sine and cosine, the two very humble functions that describe all that cyclical behavior with perfect elegance. But we're not going to stop just at the first derivative. We're going to go deeper because the second derivative tells us about the acceleration. We already know that. The third gives us insight into what was called the jerk, the rate of change of acceleration. And the fourth and beyond can help us describe complex vibrations, signals, and patterns. Trig functions are unique because their derivatives cycle back on themselves, giving us a perfect tool for modeling systems that repeat, oscillate, and resonate. So by the end of this lesson, you will have had a chance to practice differentiating more trig functions, and you'll also have a chance to interpret them in a context that involves real-world phenomenon to see how the beauty of sine and cosine runs through all aspects of the physical world that's around us. Let's start by looking at a question. So the displacement of a particle on a vibrating string is given by the equation S at t is equal to 10 plus 0.25 sine 10 pi times t. And we're going to find the velocity and the acceleration. So remember that velocity is the first derivative and acceleration is the second derivative. So I'm just going to remind you of that velocity is the first derivative. So for any equation that we're given that models some distance, some height, like this one that we have here, some change versus time, the first derivative will always be the velocity of that motion. And the second derivative will be the acceleration. So the second derivative gives us the acceleration. And we've used that a little bit when we've been looking just at regular polynomial functions. But we can do the same thing with trig functions and sine and cosine. So let's use what we've learned about sine and cosine and taking the derivative of those other trig functions and apply that to what we have here. So we have the equation S at t is equal to 10 plus 0.25 sine 10 pi t. Okay, so now let's think about taking the derivative of this. We're going to use our rules that we have to take the derivative. We've got all of this together that we can take the derivative of. So my first derivative is going to give me the velocity at any given time. Well, the derivative of 10 is 0. Now we have 0.25. Derivative of sine is cosine 10 pi t. And the derivative of 10 pi t is just 10 pi. 10 pi is just a constant in front of the variable t. I'm going to go ahead and expand this out by multiplying my 0.25 by my 10 pi. And I end up with 2.5 pi times cosine of 10 pi t. So this is my derivative to find the velocity. So if you were needing to find the velocity at any given time for this particular oscillation or particle on a vibrating string, you would be able to use that particular equation. That's our first derivative. That's the first derivative. Now, if we want to find acceleration, we're going to take the second derivative. So essentially, we're taking the derivative of this first derivative. So the acceleration at any given time t is going to be equal to the second derivative of our original equation. And so we have 2.5 pi, the derivative of cosine 10 pi t. These are mouthfuls to say these all together. Derivative of cosine is negative sine. That will be 10 pi t. And then again, the derivative of the inside here, 10 pi t, is just 10 pi. Again, I'm going to go ahead and I'm going to do some multiplication of these two values here. So my acceleration, my equation for acceleration is equal to negative 25, not 2.5. Negative 25, and the negative comes from the fact that I'm bringing this negative out of inside there. I can multiply that out. It's just like a negative 1 in front. So negative 25 pi squared, because I have pi times pi. So 10 times 2.5 pi times pi. That leaves me with sine 10 pi t. So if we know the time at which we're trying to figure out this velocity and the acceleration, we now have the first and second derivative to be able to determine that. Okay, let's look at another one. A mass pulled down on a rubber band and released has a motion modeled by the equation 2 cosine t plus 3 sine t. And if you could imagine what's happening there, if you could imagine that motion. So we've got an elastic band being held up maybe by a retort stand, and you've got a mass hanging on here. And maybe if you took physics when you were doing oscillations, maybe your physics teacher would have shown you this. But what's going to happen is if I pull down on this, you can imagine the elastic band is going to stretch, and this mass is going to start vibrating up and down or oscillating up and down. So that's the motion that we're talking about. So a mass pulled down on a rubber band released has a motion that's modeled by this equation, 2 cosine t plus 3 sine t, where s is measured in meters from rest downward and t is in seconds. When will the mass first reach a maximum downward displacement? So this maximum downward displacement is what's telling me what we're looking for. So we need to find that first derivative to find the max. So that's what, to find a max or a min, Okay, so let's get to doing some of this math. I'm just going to make this a little bit bigger and pull it up a little so you can see it. So our original equation is s 2 cosine t plus 3 sine t. Now, remember from when we were working with polynomials, if I want to find the critical points, which is really what I'm doing, I take the first derivative and then I set that first derivative equal to 0. So my first derivative of 2 cosine t plus 3 sine t will be negative 2 sine t plus 3 cosine t. Derivative of cosine is negative sine, derivative of sine is cosine. So there's our first derivative. We are going to set this equal to 0. So set equal to 0 to find the critical points. So 0 equals negative 2 sine t plus 3 cosine t. Now we're really not going to do anything with this but solve it algebraically just by moving some things around. So I'm going to move this negative 2 sine t over to the other side to become positive 2 sine t is now equal to 3 cosine t. Now we're just going to reverse order it, reverse bedmass. So now I'm going to get rid of the 2 in front of here because ultimately I want to solve for t. I'm going to get rid of the 2. So sine t is equal to 3 over 2 cosine of t. Right? We can write it like that. There's nothing that says we can't. Now I want to get rid of this cosine over here. So I'm going to divide by cosine. So now I have sine t over cosine t is equal to 3 over 2. So now we're getting somewhere because we know that sine over cosine is equal to tan. So tan of time is equal to 3 over 2. If I want to know what t is, I'm going to use the inverse of tan. So t will be equal to my inverse of tan of 3 over 2. And that's going to give me a value approximately equal to 0.98. But remember, this is oscillating. So there's actually going to be 2 times where it's going to have a possibility of being at a maximum. There'll be 2 points. So we have to add pi to this to get the second point, because remember, it's oscillating. So our second time would be 0.98 plus pi, or 4.12 seconds, approximately 4.12 seconds. So now we need to determine, now that we know our 2 points of 0.98 and 4.12, now what we need to do is we need to confirm which ones are maximums or which ones are minimums. And remember, to do that, we use our second derivative test. So now we found the critical points. Now we're going to use the second derivative test. To determine maximums for max / min. Since we have 2 points, we need to figure out which one is which. So we're now going to find the second derivative. And the second derivative of -2 sine t plus 3 cosine t is going to be -2 cosine t minus 3 sine t. If you're unsure about how I'm getting those derivatives, go back to the first 2 lessons that I posted last week, and that will go through for you how I'm getting these derivatives, where they're coming from. So now what I'm going to do is I'm going to plug in my values. So what is the value of my second derivative when my time is 0.98 seconds? And if we plug that in and plug it into the calculator, we will find that it is actually less than 0. That value will be less than 0. That tells me then that this point here will actually be a local max. But we have 2 points, so we have to see what's happening at that other point, and the other point is at 4.12 seconds. If we plug that in to our equation, to this equation here, we get a value that's greater than 0, so that tells me that 4.12 seconds is going to be a local minimum. So, to answer the question, we now can say that a local maximum, when the mass first reaches its maximum downward displacement, will be at 0.98 seconds. So now we've looked at a couple of examples where it's been business as usual, first derivative, second derivative, but I think we can start to see that this oscillating mass on this elastic isn't going to stop just at 1 or 2 oscillations. It actually is going to continue going. We need a method to be able to determine oscillations and derivatives many, many times removed from the first and second derivative. What would be the 31st derivative? What would be the 103rd or 257th or 1/1,000,000th derivative? And when we have oscillating motion or vibrations, they aren't going to stop. They are going to continue to keep going, and we can get a lot of information from those patterns. So the good news is it's actually not all that hard to do. It sounds daunting, but it really isn't, because like everything else in math, and especially in calculus, there are patterns to what is happening. So let's look at an example just of the process. And then we're going to look at an example that has a little bit more of a real world meaning. So if we are needing to find the nth derivative of sine or cosine, it doesn't matter, the nth derivative, just any of them, of sine or cosine. So let's say we need to find the 30th derivative of y equals sine. So we're going to start by doing what we always do, and we're going to take the first derivative. So my first derivative of sine is cos x. My second derivative is, so now I just take the derivative of cos x. So my second derivative is negative sine x. And what we're going to do now is take the derivative to find the pattern. So what we're looking for here is we're going to keep taking the derivative until it goes back to the original function, until we get back to y equals sine of x. So there's my second derivative. My third derivative, the derivative of negative sine x, is negative cos x. Now my fourth derivative, so the derivative of negative cos x is negative negative sine x, because the derivative of cos x is negative sine x. So now, if we take a look at what's happening here, this is actually equal to sine x. We have returned back to our original function. So what we need to do is we need to take a look and we need to say, okay, well, what's the pattern here? So the pattern is repeating. Every fourth derivative goes back to the original. So we're going to use this pattern to figure out the 30th. So now 30 is not divisible equally by 4, so I can't divide 4 by 30, but I'm going to look for the next closest derivative before that is. And 28 is divided by 4, can be divided by 4. So I know that my 28th derivative will be back to sine x. D30, or derivative 30, is 2 more down the pattern. So 1, 2 more down the pattern. So this would be derivative 29, and this would be derivative 30. So we can say that the 30th derivative of sine x is equal to negative sine x. So it really is as simple as finding the pattern. So we can do this for any number of derivatives so long as we find the pattern. It's just a matter of finding the number that's divisible by that. So this rather unassuming question of determine the 103rd derivative of cos 2x, so what is the 103rd derivative, actually does have a real world scenario that can be attached to it. So imagine you're working at an engineering firm that's designing ultra-sensitive sensors for vibration analysis in spacecraft. Space is something that's very near and dear to my heart. I know you guys don't know me very well, but did always want to be an astronaut. That was my pathway when I was at university. So vibrational analysis in spacecraft, that's what you're working on. These sensors monitor tiny oscillations in various components, the solar panels, the antenna arrays, as the spacecraft travels through space. And these vibrations are modeled using trig functions very similar to cos 2x, where the variable x might represent time or position along a flexible structure. So to calibrate the sensors, you're going to need to analyze not just how these components move, the first derivative, or how they accelerate, the second derivative, but also how their vibrational behavior evolves or changes through many levels of responsiveness, in this case up to the 103rd order of sensitivity. And this is crucial for detecting resonance frequencies that could, over time, lead to structural fatigue or failure. So this is what we're going to do right now, is we are going to determine the 103rd derivative of cos 2x in this imaginary scenario that we've developed here of spacecraft sensors. So we're going to start by taking the derivatives one at a time until we get back to the original and then find the pattern. So my first derivative of cos 2x is negative 2 sine 2x. Remember, derivative of the inside times the outside, and derivative of the outside. Okay, so that's my first derivative. My second derivative, I now have 2 times negative 2. So I have 4. Sine becomes cosine. My 2x stays the same. So now let's take the third derivative. 1, 2, 3. Again, multiplying that 2. This will become negative sine, so that becomes negative. So negative 4 times negative sine becomes positive 4 times 2. That becomes 8 sine 2x. Our fourth derivative in this case then will become 16 cos 2x. Now, you might be thinking we're not really seeing a pattern here. And the reason we're not seeing a pattern develop is because our leading values are constantly changing. This is where we need to start thinking about these as exponents with a base of 2. So our second derivative here would be, we could say, is negative 2 to the power of 2 cos 2x. Our third derivative, 8 expressed as a power to the base of 2 cubed sine 2x. 16 is 2 to the power of 4 cos 2x. Are you starting to see a pattern here? So our fourth derivative, 2 to the power of 4 cos 2 to the x, we now are back to our original function. So now we're going to look at within this pattern for our 103rd derivative. So again, the pattern is based on a pattern of 4. 100 is not divisible by 4. So we have to, 103 is not divisible by 4, but 100 is. So we know that this would be D100. So if we go back up to the top, this would be D101. We have D102. And here we have D103. So our winner for the 103rd derivative is our 2, is this pattern. Sorry, there is a little bit more to it. So we know that D100, I'm just going to back it up a little here. D100 is equal to 2 to the 100 cos 2x. But that's not what we need. So we need to count up from there to 103. So my 103rd derivative will be equal to 103 sine 2x. Sorry, I backtracked a little bit there because I realized I forgot to tell you. So when we're looking at these patterns, this is my 2 to the power of 4. This was my 4th derivative. 2 to the power of 3. This was my 3rd derivative. 2 to the power of 2. That was my 2nd derivative. If we wanted to, we could say this was 2 to the power of 1 sine 2x, and that would be just 2 raised to the power of 1. So now, without having to do 103 derivatives, we have been able to determine the 103rd derivative in order to be able to determine what these sensors, how to calibrate these sensors to analyze ongoing oscillations.